Thank you. As always, there's always inaccuracies. That's my fault. It's now 30 years at IBM. I was born back in a decade where people called us baby boomers. And I originally studied applied physics and electronic engineering, and also computer science back in the days when there wasn't computer science, one of the very first degrees offered in computer science. And then I did a PhD in information theory. Information theory is basically, it's group theory, number theory, a lot of kind of abstract and convoluted mathematics. And little did I realize way back then that actually 35 years later, so I did my PhD 35 years ago, 35 years later, I would have a renaissance based on what I studied and all the stuff I learned back then, because actually with that, armed with those tools, you're pretty well armed to understand, or at least to attempt to understand, because nobody really understands it, quantum physics, quantum mechanics, and quantum computing. So I'm going to talk about IBM's quantum computing platform, including things like QuizKit, the IBM Quantum Experience, and hopefully open some doors, make you think about what IBM's doing in this space, and of course the appeal to everybody to contribute, to work with us. So let's see if this works. So I guess the fundamental question is, have we reached, and this is our IBM Quantum Cat, the Quantum Cat. He's thankfully alive and not in superposition, and certainly not dead. Have we reached the limits of classical computation? So let's have a look at. Yes, I've been practicing this. I can see are you all impressed? Yes, this is 30 years working for IBM, practicing with Microsoft. Is there anybody from Microsoft here? Microsoft is a love-hate, yeah. It's good for some things, but let's see what happens. I can hear the intake of breath here, like, how did he do that? It's quantum. So this is everybody's contemporary view of quantum computing. For those of you who are observant, you've seen me before. I was sat on the step here doing some stuff, so I was quickly writing my foils. I just pulled these literally about 3 minutes old off Twitter. I thought that was quite nice. So we have, we have the picture of the chandelier, and it's cold, and it's even more cold, and down at the bottom it's really, really incredibly cold. And then we have some means of mapping some real-world problem onto probably a Hamiltonian, probably using the Ising model, and nobody understands what the hell it's all about, but it seems to work. And of course, between this, I'm British, I'm allowed to be humorous, or at least I'm allowed to attempt to be humorous. Between this level and reality, there was a kind of mapping and some details we need to understand. If we take a look at quantum algorithms in general, and we've heard some talks today about different approaches, how we might actually use quantum computing, but fundamentally we've got to actually understand a lot about how contemporary current algorithms work, what their limitations are, and how quantum computing might be able to improve that or bridge that gap. Is there anybody here with a background in theoretical computer science? Okay. So I'm thankfully for the rest of you, and thankfully for me, because the theoretical computer scientists will be able to pick holes in it. I'm not going to go into a complete derivation of the BQP hierarchy class derivation, but it really, in order to understand quantum computing, or the advantages, potential advantages of quantum computing, you need to understand at least a little bit about theoretical computer science and algorithmic performance. In particular, as we'll see later, one concept which is quite key is the idea of a quantum computer providing a supra-polynomial speedup. Okay, it might be an exponential speedup. It might be something else. It might be supra-exponential, but it's at least supra-polynomial. And we'll see why that's important in a few minutes. This is a foil which does not display. Also not. Okay, so if we look at the class of algorithms which we're attempting to address with quantum computing, we have so-called easy problems. Does anybody know how we classify or name those easy problems? Anybody got an idea? Polynomial. For those of you, for the computer scientists, close your ears. For the rest of you, these are so-called polynomial time algorithms. So they're algorithms which are a polynomial in the size of the input, whatever that means. Yeah? So classically, multiplying two numbers together is polynomial. Just in order to do that, I need a number of operations which is a multiple of the size of the two numbers I'm trying to multiply together. We all know, we've all heard, or we should have all heard of Shor's algorithm. Who hasn't heard of Shor's algorithm? A couple of people. Okay, Shor's algorithm is a quantum, it's an algorithm which can be run on a universal quantum computer, which provides a supra-polynomial speedup of factoring numbers. So multiplying numbers is polynomial. Determining if a number is a prime, does anybody know what that is? It's polynomial. Factoring a number, an arbitrary number, into its prime factors is? No, it's not polynomial. That's the whole basis of cryptography, or at least most public key cryptography relies on the fact that that is a super polynomial. And Shor's algorithm, unfortunately, can factor in polynomial time. There's a kind of a small gotcha with Shor's algorithm. So for, let's say, realistic numbers, realistic sized numbers, you are almost certainly going to need tens or hundreds of millions of qubits. Currently, the best universal qubits, the best we can achieve is less than 100. So we're a long way away yet, but maybe one day that will become feasible. The original use case for quantum computing was to simulate quantum mechanics. That's also a quantum easy problem. Somebody earlier talked about how you can map, in particular, optimization problems using the variational quantum eigensolver onto a Hamiltonian equation. Hamiltonian equations are things you can relatively easily solve, or at least observe, with a quantum computer. So there are some ways to approach specific problems. But in general, we're looking for hard problems. No? Typically, these are problems in the area of algebraic and number theoretic problems. Also, optimization problems. The optimization problem one is one of the most interesting ones. And if I look at the space of developers, startups, people who are actively working on and with, and especially with quantum computing and our APIs, there's a lot of companies in there in the finance space. Because if you look at hedging or portfolio analysis or economic prediction, these are all fundamentally optimization problems. So there's this idea that when we get to quantum advantage, suddenly problems in the financial space or logistics, which are intractable today, will become tractable, and I'm sure that will happen, and a result of that will be complete change in business models and how these industries work. Machine learning, I'll talk a little bit about that in a second. And of course, simulating quantum mechanics for chemistry, which is the area where we expect quantum advantage to occur earliest. Just to illustrate this, I don't know if anybody's seen this. I merely must apologize for HDMI and my this is, okay. 26,000. So the question is, the question was, okay, the IBM Blue Gene Q, now, supercomputer. It can, this stuff you can't read, it's saying, so for a 512-bit number, how long would Blue Gene need to factor that? And the answer, which you can clearly see here, is 26,000 years. Okay, oh, it looks better. How long would it need for a 1024-bit number? Anybody want to hazard a guess?
Yeah.
Exactly. Take Shor's algorithm. That's the speed up. So that's superpolynomial speed up. The small qualifier of this is that you need a fault-tolerant quantum computer with around somewhere 10, 20, 30, 100 million qubits. So we're still not there yet. How do we actually program a quantum computer? Now, there are a variety of approaches, but fundamentally it comes down to mapping in some way your problem onto an interference pattern, which is, in this interference pattern, you set it up on your qubits. There are two mechanisms for doing that setup. There's superposition and entanglement. So superposition, we've seen, the block sphere, where you put a initialized qubit into a superposition of two states. An entanglement is where I make two different qubits into one system, one quantum mechanical system. And the real challenge is, given a real-world problem, for example, invert a matrix, how can I map that into a bunch of these types of operations? There was a question somebody asked earlier about different types of Hamiltonians. Who was it? Somebody sat up here. Yes, you were asking about new Hamiltonians. Right now, we have the superposition, the Hadamard transform, and the C0 transform. Those are things you can more or less easily implement in hardware, but obviously there's a lot of people working on, I would say, higher level fundamental Hamiltonian operations, which would, were they to exist, would also result in speed up in algorithms. So we take a superposition of all the states. This bit is a lie, because in order to visualize multiple qubits with entanglement using the block sphere, it quickly becomes a problem that's only understandable by pangalactic transdimensional hyperbeings. I'm allowed to say that here because you're developers, and I can assume that some of you at least have read Hitchhiker's Guide to the Galaxy. Who hasn't? So for the video, there was about 3 people put their hand up, and all the rest have read it. So you know what the mice are, right? The mice and the okay. So only the mice can understand the hyperdimensional block sphere mapping. There is a way to do it with 2 qubits, but it's extremely convoluted and not really very intuitive. Basically, we have a way of entangling the qubits and making out of a, for example, 20-qubit quantum computer effectively one consistent quantum system. And then the magic happens where we basically collapse the wave function we observe, and out pops the result. Every quantum computing program, and I don't know if that's people really understand that, which is why I'm going to emphasize it again. Every quantum computing program is actually a circuit, so it's initializing a bunch of bits, performing some preparatory operations on those qubits, and then observing. There's no feedback. Feedback is forbidden. So reversibility and no cloning, two principles of quantum computing. The output of this quantum program is non-deterministic. It's fundamentally non-deterministic. That means when you perform your experiment 2 times, 3 times, 4 times, 5 times, you never guarantee you'll always get the same result. If you're lucky and your algorithm is robust in non-determinism, then you get a very, very clear statistical correlation showing you one particular result. And then assuming your algorithm is designed well, you know, okay, that's the answer. There are also inherently in all quantum computers, because even though, as we saw, the quantum computer is very cold, and it's under high vacuum, and there's very little electromagnetic radiation impacting on it, it's still not perfect. So every operation on a qubit, whether it means putting it into superposition or entangling it or even reading it out, also introduces, by its very nature, because it's an interaction, introduces additional errors. And that, in fact, that's one of the major challenges in actually building real universal quantum computers, is to manage and handle those errors and keep them as low as possible. When we talk about the power of a quantum computer, it's not just important to talk about the number of qubits, because you know, what would 200 qubits, what benefit would they be if the individual qubit error rate completely dominates any calculation? Otherwise, the 200 qubits would be useless. I need to have a corresponding error rate which is correspondingly low in order to be able to actually make use of that. So there's always a trade-off between error rates in fundamental simple operations, in entanglement operations, in readout operations, the coherence time of a quantum program, which also, of course, determines how errors can add up, how errors are combined, and the number of qubits. At IBM, we talk about the quantum volume, which is a measure of number of qubits and the error rate. Also of considerable interest is the coherence time, because that determines the maximum amount of time you have for your quantum program. And coherence times of the order of tens or maybe 100 of microseconds are normal. When you think about it, back in the day when Deutsch, Feynman and Deutsch were thinking about the principle of a quantum computer, and that we might need such things, I can vaguely remember it. I was doing my PhD, early 80s, and I can remember this stuff about, you know, the idea of a quantum bits, and I've not looked it up. Maybe I have to do that, but I seem to remember that way back then, the first attempts, the coherence times were measured in femtoseconds. So now we're in tens or maybe even hundreds of microseconds. So we're a long way. It doesn't sound like a lot, but it's actually a significant development. So historically, quantum computing was the domain of quantum, say, the quantum scientists, physicists, chemists. We're now at the phase where we're quantum ready, and we see this. IBM, our competitors, I don't like the word, our, in German, Mitstreiter, the people in the market, in the quantum computing market with us, we all see a very, very big uptake, great interest in quantum computing. And right now, the challenge is to understand how to program quantum computers, to demonstrate as early as possible quantum advantage. And there is significant economic and business interest and impact on doing that. And at some point in the hopefully not so distant future, we will be in the phase of quantum advantage. So this is a model or a mock-up, or actually it might be a photo of the one they actually built. I think it is. Anybody know this? Of course, you're developers, hackers, you know it. So this is Charles Babbage's computing machine. It's one component of it. It was never built because back in 1823, I think, or 1833, they did not have the metallurgical skills to produce gear wheels of sufficient strength and accuracy. It's, I don't think it's a Turing machine, but it's pretty damn close. It's a Turing machine, but it's a Turing machine, but I don't think it's a von Neumann architecture, but it's very close. So it has a CPU, has registers, it has the idea of memory. A mechanical von Neumann machine from 1823. So when I'm English, I'm British, and I've been living in Germany for 30 years. So one day after Brexit, literally one day after Brexit, I applied for German citizenship. So I'm now German and British. So when my German fellow Germans, they all say, well, Konrad Zuse invented the computer, and I pull this out and say, nah, sorry, not gonna, no. All the best ideas that come from British people, which raises a very pertinent question about what the hell Brexit is. Here I am in the centre of the what was this? This would be the was in Star Wars the Death Star. So Brussels will be the Death Star with the EU Commission. I'm very pro-Europe, by the way. Anyway. So and this is where we are right now. So there are several of these, an undisclosed number, sitting at a couple of locations, IBM locations. You may have seen in the press at CES a couple of weeks ago, we announced the first, I would say, commercially available quantum computing system. So that's significant because that means we are moving from a pure research model into a model where we're actually going to work with customers on developing applications. And we use for our qubits, we use these babies here, superconducting Josephson junctions. There are several other approaches, some of which are actually in current use, some of which are currently only of theoretical interest because nobody's actually observed them. Specifically, the entanglion approach. If anybody's not heard of entanglions, go Google it afterwards. Entanglions, if we actually show that they exist and are able to use them, they will represent a very, very interesting technology for the basis for quantum computing. The key point here is that the underlying technology, the methods of mapping quantum programs onto a specific technology, and the method of mapping applications onto quantum programs, these three levels, we want to see these decoupled from each other. So such initiatives as OpenQuasm for the layer between the quantum assembly language and the hardware, open standards for how you actually control and operate a physical quantum computer, and also standards for how compilers are built. That's all open source. I'll show you in a minute how to get access to it. There's SDKs and APIs coming out of your ears on GitHub. But so the important point here to note is this number here. Any electrical engineers or electronics engineers here? Yeah. So you know, Boltzmann's constant. Particularly at microwave frequencies, you have equivalent temperature, and noise floors, and all that sort of stuff. So before I came up here, I was down at the amateur radio bench down there, and because I'm a radio amateur as well, so talking to the guys about moon bounce and that sort of stuff. So this is all very important when you're working at microwave frequencies, low noise, and that's actually one of the reasons why the quantum computer has to be so cold. Is that you need the noise, the environmental noise around the qubits to be lower than the value, the equivalent temperature value of the 1 or 0. And there we go. So 100 micrometers is here. This device is, I guess, a few nanometers. Does anybody know if I have a gate, a physical gate on a chip with a size of, let's say, 10 nanometers? Anybody know how many silicon atoms are in there? I'm looking to the electronics engineers. 50? No, it's more. It's about 50 or 60. But it's still a sufficiently small number of electrons, of atoms that you don't observe. Your gate is almost dominated by quantum effects, especially at room temperature, which is why Moore's law is basically, at least the scaling of gate size is breaking down. The die size expansion is also kind of hit some limits. So that's what one looks like, or at least an IBM one. If you remember the photos from Rigetti and D-Wave, their quantum computers look astoundingly similar. That's not chance. That's kind of the way you have to do it. The thing I always found fascinating was see these little stripes here? And you can't see it down here. There's this sort of big block of thing here and some stripes here. It goes all the way up to the top. So the whole thing is cooled with helium-4. Helium-4 is the common isotope of helium. Helium-4 has a boiling point of, I think, somebody probably going to correct me, about 3.5 Kelvin. There's an isotope of helium called helium-3, has 1 neutron less. Its boiling point is around 2.7 Kelvin. You use the difference in a refrigerator to basically freeze down to 10, 15 millikelvin. Interestingly, the amount of helium-3 on Earth is rather restricted, and it doesn't occur very often spontaneously. So there's once you've put the helium-3 in the fridge, you don't let it leak. It's expensive. So we saw one of these pictures earlier, 15 millikelvin down at the bottom, a bunch of microwave electronics. What actually happens inside there, input-output modules, a whole bunch of control electronics here. What you're seeing there is a photo of one of the research machines. Obviously, in a commercial quantum computer, a lot of that's going to be miniaturized, and I'm sure at some point in the future you'll have a pizza carton control electronics for your quantum computer. For those of you who work in compute centers or in computing delivery, you know the term pizza carton. This is the affectionate term for the CPUs and memory and disk things you put into a 19-inch racks. They're called pizza cartons. So I'm sure that will be a pizza carton to control electronics at some point. And then, of course, compilers, APIs, SDKs, and cloud access, and HTTP wrappers, and all that sort of stuff. And so the idea is that we were going to replace this with this. Actually in a certain way, and I was at, where was I? I was in Berlin yesterday, in Potsdam, the Hasso-Plattner Institute. And they have a museum of computers there, so some very, very old PCs, you know, so VAX and PDP-11 and all this sort of thing. And the really, really old computers, you won't remember it, I do, but to initialize the computer, to boot a computer, you had to physically enter the actual first memory locations by hand. It's actually it's a very good analogy for how we initialize and set up qubits. You have to do it manually. But a lot of people working on quantum memory and quantum sensors, I'm sure that problem will at some point in the future also, if not go away, at least be mitigated and improved. So this is the bit where you roll your eyes because it was going so well before, and now he's not done it. So the key thing is I need to get the little here we go, there we go. No, I already did this. Oops. Okay. Here we go. So how is IBM working with quantum? So there is a whole bunch of stuff on GitHub. There are various APIs, but what we've said is that basically a couple of toys and giveaways, and there's an app for iOS. There's even a board game called Untitled, which is actually quite fun and undergoing revisions. And we've developed a Model Q keyboard. I'm not quite sure what the point is, but it's selling like hotcakes. If you don't like Jupyter notebooks, if you are the strange kind of person that doesn't like Jupyter, is anybody here who doesn't like using Jupyter? I knew it was going to be you.
Yeah, sorry. I use it, but I don't like it.
Yeah. So you're obviously one of these people who insists on using Microsoft VS Code. Yes, we've got you covered. So if we look at this separation, so Qiskit Terra is basically, it's the gate level. So in Qiskit Terra you can do a Hadamard transform, you can do a C0 transform, you can do XYZ, so you can do the Dirac manipulations. So it's very, very low level quantum computing. It's really simple to install, pip install Qiskit, that's it. You need an API key. I'll show you how to do that in a second. Then we have something called Qiskit Aqua. And Qiskit Aqua is interesting because nobody's really kind of addressed that, but what would it be like if I had, for example, in Python, an API call which said, calculate binding energy. And I give it, open brackets, I give it my API key, and then I say, hydrogen, lithium, hydrogen, close brackets. So where's the quantum computing? I don't care. You know, maybe I'm using the quantum computer as a backend, maybe I'm using a quantum computer simulator, maybe I'm using a classical supercomputer, maybe if it's only hydrogen, lithium, hydrogen, I'm using my laptop. But if it's a caffeine molecule, I'm using the quantum computer. So for IBM, it's clear to us that the level at which you ultimately use quantum computing, you're not going to have to take care of are there actually qubits down there or not, and that's the level we work with Qiskit Aqua. We also have Qiskit Air, which is also open source, publicly available. This is for access to and working with a quantum simulator. There is a open source, publicly available quantum simulator out there. You can use that. IBM has a variant of this that's behind Air. There is also Qiskit Ignis. Qiskit Ignis is or at least parts of it are in Qiskit Terra. Qiskit Ignis, you get the analogy. Ignis is like the magma and hot rocks underneath the Earth's crust. So Qiskit Ignis is all about manipulating and working with actual individual qubits and the technology itself. So it's below the waterline or below the crust of the planet. We have a number of publicly available quantum computers. Tokyo isn't publicly available. Tokyo is only available to our customers. However, Melbourne and the other quantum computers are publicly available. You can go, on the QuizKit website. You can see I just did a screenshot about an hour ago. So you can see the current operating frequency. So if you remember beforehand, the 240 millikelvin, the equivalent is the equivalent noise temperature of a 5 gigahertz signal. We're operating at 4.9 gigahertz. You can see the related timings for Tokyo, so coherence times. You can see gate errors and readout errors, and we make that all publicly available. We're very open about that. Why are we open about that? Because that actually determines the performance, or it determines whether your quantum computer is, your quantum algorithm, your quantum program is actually going to work or not. In fact, the compiler that sits between QuizKit Aqua and QuizKit Terra, you can tell it, I don't really care which physical machine you use, just give me the one with the shortest queue, or give me the one with the lowest error. If you look at the this is the topology here. So this basically says that qubit 0 and 1 can be entangled with each other, but 0 and 6 can't. Yeah, they can't. So where there's a connection, there's entanglement possibility. Interestingly, this one here looks totally different from this one. So Melbourne is a kind of, it's like a very, very linear. Tokyo is a mesh. Wouldn't it be nice if at least at the application level, the compiler took care of that and said, well, just give me your topology and I will map it to whatever is available. So we also do that. Go on to GitHub, please. It's all open source. Hack it, improve it. It's being recorded, so I hope nobody from IBM sees this. But we've had a lot of input from people outside IBM who've made some of the software significantly better. Okay, you're all developers. I'm allowed to say that. Nobody's going to hoist my petard for that one. So you can see up here, there's 177 repositories in total working with and on and related to QuizKit, and around 2K commits. So we have some people out there working very actively with this on developing this software and using it, but actually developing the API itself. If you want to sign up, then, and you're a student or a faculty member or a PhD student or whatever at any accredited academic institution, please go via On the Hub, sign in there. If you're not in that category, so if you're a working developer earning real money with a real job, then just go onto the quizkit.org. It's all free. We also have some interesting collaboration possibilities for developers, for startups. If you want to talk about that, just let me know. And I would say with that, how many minutes have I got left? One.
1 plus questions for 1 minute.
Okay, so at that point, I have got about another 300 foils. Seriously, I do have another 300 foils, but they go into things like machine learning optimization in some detail. But I think that's enough, at least initially, just give you a feel for where IBM is. And I'll take some questions. Yes.
The thing is that the internet is not directly connected to the IBM quantum computing, but I read in the internet is a preparation of talks a day of some Gil Carlyle, who said that at some point we expect quantum computers to run into fundamental noise problems. Have you heard anything about that?
So the question was, you'd heard of or seen something about a comment that all quantum computing problems will be, what was it, quantum?
One was kind of that to combat noise, quantum computing works as qubits. but every qubit kind of increases noise level, and he predicted it to be exponential.
Yeah. Okay.
So kind of at some point you add more noise than you find.
Yeah, I'm familiar with this. This is the noise beats everything principle. Unfortunately, I'm not into that enough to be able to comment on the validity of it. Or, I mean, speaking as an engineer, I understand the argument. However, back in the 1960s, when I first took a soldering iron into my hand, and I look at the size of integrated circuits back then, and the performance, and the Intel 4040, which was the first 4-bit microcomputer on a chip with a clock frequency of, I think, 60 kilohertz, and the performance figures and noise figures and capabilities, and compare that with the couple of billion transistors on this, I wouldn't want to bet on noise. I mean, noise is always a problem now. You can't get away from it. But I think where we are currently with the noise ceiling, we're going to push that way, way back. So there was another question. Hold on. Here.
So I wanted to ask about the quantum volume. So
yes.
What's the quantum volume of current chips?
Yes.
Like your, for example, Tokyo?
Yes. Well, of course. Well, the question is, he wanted to ask about quantum volume, and what's the quantum volume of our current chips, like Tokyo, the best in the market, of course. No. Yeah, we think we're among the best. No. I mean, what quantum volume is exactly? There is a formula, and you can think about, like qubit equivalent or noise equivalents. Ultimately, it's the idea is just to have an awareness of it's not just the number of qubits. Yeah, you could make a chip right now with lots and lots of qubits, but it'd be useless because noise would dominate. You need to do both. So hold on. Before the question here, there was a question back there.
Oh, yeah. Can you talk more about Qiskit Aqua and how that chemistry API works? Like, how were you able to implement something that's so general?
Can I talk about Qiskit Aqua and how the chemistry API was implemented? Yeah, that's a 3-day intensive course at university. Basically, if you're developing quantum algorithms, you have 4, maybe 5 ways to do it. The one's already been mentioned is using oracles. So can I decompose my problem into such a simple fundamental building block that I can reproduce it? Scott Aronson, the father of computational complexity theory, would be shooting me right now for claiming that. The second way is can I adapt my problem to a Hamiltonian of some kind? We already saw that with so D-Wave are using that, but Rigetti, everybody's using that, using the variational quantum eigensolver. Take my problem and map it to a Hamiltonian. The third way, Peter Shaw kind of did it without realizing it, is there's this really nice thing, and if you're an electronics engineer or a communications engineer, that's the point where you have Erleuchtung, enlightenment, is that the Fourier transform, which is in the real world sucks computationally, and a quantum computer is a thing of beauty. It's fast and it's simple. So if you take the hidden subgroup problem, which says I've got a group of things, are the two subgroups which are isomorphic, which map 1-to-1 to each other. It's a combinatorial problem. Basically, to answer that, you've got to look at every possible subgroup. So for a group of size n, it's 2 to the n computational steps. The quantum Fourier transform, you just do a Fourier transform of it, and you see, zack, all the isomorphic subgroups appear as like frequencies when you do a normal Fourier transform. That technique, you can use that to do phase estimation. With phase estimation and arbitrary rotations, you can do the HHL algorithm. You can do matrix inversion. So you take a Gaussian elimination, which is n cubed, and turn it into HHL, which is log n. There are a few other techniques. somebody standing up, which means I've got to shut the hell up. If you want to talk about that, if you want to learn about that, if you want to work on that, sign up. There is a Slack channel. There's a whole bunch of IBMers on the Slack channel. We're very happy to talk to you. Have I got to stop now?
Yes.
I'm around today and I'm around tomorrow, so just hit me if you've got questions or you want to know more.